Hello, algebra students. We're getting to the end of our overview of quadratics unit that we've been working with, just kind of how quadratics work and what they look like, that kind of thing. So this is just a quick review of what we've done in all of the sections that we covered in this chapter. So I'm going to ask if you can write an equation or recognize an equation that's linear. Remember, linear we spend a long time on. That's stuff that looks like slope-intercept form. So you could write an equation that looks like y equals 5x minus 10. That is linear. That would be a straight line. If I ask for something that's quadratic, quadratics have squares. We've talked a lot about squares in patterns or in the equations. Most of the stuff that we've been working with all have something getting squared. So I would have something like y equals 2x squared. And then you can add or subtract something else if you want to, but you don't even have to get fancy. I need something with an x squared. And something that's neither of those, I would say an easy thing to do is just change the exponent. You know, in linear, I don't have an exponent on the x. There's really a 1 there. Quadratic is a 2. Linear, or neither would be something like just x cubed. And again, you could add or subtract other stuff after that. But having something that's not an exponent of 1 or an exponent of 2 is going to give me something that's neither linear nor quadratic. If I ask you to sketch a graph, so linear, again, I'm just going to show all of these, and I should have left more space. Something that looks linear would just be on a graph like this, something a straight line, right? That's linear. Quadratic has that shape of a parabola that just kind of do this kind of thing. That's quadratic, right? It's that U shape, either upside down or right side up, but it's that U. And neither would again be something that's just not one of those, right? You can have something like that even. That is definitely not linear or quadratic. A pattern. Something that's linear for a pattern, we could be looking at, let's say just this. So I would start with 1, and then my next one would have 2, and then my next one would have 3, and then we'd have 4, right? It's increasing by 1 every time. It's adding something every time. That's a really basic linear pattern. To have a quadratic pattern, again, we're looking for squares. So just keeping it as easy as possible. We can say 1 squared, 2 squared, 3 squared, and 4 squared would be 16 of those. Right? So that would be a quadratic pattern. Something that's neither just can't have this. Now, we do have things like exponential functions, but a really easy thing that you could do for neither for a pattern would be, all right, what if I have 1 and then I have, let's say 4, and then I have 2, and then I have another 1. Like there's really no pattern there that's obvious. Maybe if I had a longer pattern, I could see it, but it's clearly not linear where we're adding. It's not quadratic where we've got something getting squared. Next, to write expressions that represent these different patterns that we have. So sometimes when we don't have anything for step 1 or step 0, or sometimes we have, ignore that for a second. If I would look at number 2 here, if I would have this, that would be a 2 by 2 square. This would be a 3 by 3 square. So if I said it would be the step number squared, but I'm taking away that 1 square in the corner, does that work for step 1? Well, 1 squared would be 1 minus 1. Oh yeah, that's why there's 0 there. So that would be one way to write that pattern. If I look at this one, so this is step 1 has 2 squares. Step 2 has 4, and I know that you're seeing a square right there. Oh, but this one isn't a square. This is only 6, so it's not a 3 by 3 square. It's not just like adding something onto a square either. That's not working. However, it does seem like this would be 2 times whatever step number I'm on, right? Oops. So 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. So that pattern is linear. It's actually adding on 2 squares in every step. Okay, how about this one? This one, I know the purple is kind of dark, so it's kind of hard to see the lines. But let me give you my hint that I always give. All right, so the first one is 1 squared plus an extra 1. Then the next one is 2 squared plus an extra 2. And then I've got 3 squared plus an extra 3. So this would really be n squared, whatever step I'm on, squared. That's what gives me the square that I've got outlined. Plus, each time, yes, it's increasing by 1, but it's really adding on whatever the step number is. Here I added 1, here I added 2 for step 2, here I added 3 for step 3. We've seen this pattern before, but again, let me use my same hint that I keep using. Each one of these, I see that it's adding those corners on, right? So each time I have an n squared, 1 squared, 2 squared, 3 squared, so n squared. But this time I'm adding on 4 each time. This one is a little bit more difficult to see, I think. Let me start with, I know it looks weird for me to just outline all 3 of these, but I want you to see them as 3 individual squares. And then I've got 3 more of those squared, but not the 2 by 2 square. And then I can get 3 by 3 square 3 times. So each one of them does have an n squared, but they're happening 3 times. This would be 3n squared. Now, I would like you to be able to draw a pattern for n squared plus 1. We had one that looked like n squared minus 1. When I have n squared plus 1, that means, so for step 1, for instance, I would have 1 squared plus an extra 1. For step 2, I would have a 2 by 2 square plus an extra 1. And for step 3, I would have a 3 by 3 square plus an extra 1. Oh, that wasn't very squared, but that's an example of what that pattern could look like. You could do that with dots, you could do it with sticks, you could do it with anything you wanted, but we just did a bunch of them with squares, so I just kind of stuck with squares on that. Okay, if you have 60 feet of fencing and you're going to enclose a garden, and again, we're making a rectangle, and hopefully you know already what shape we should be looking for the greatest area. But if I give you the lengths, you should be able to find the widths. And remember, if we have 60 feet total for the entire perimeter, if I add one of the lengths and one of the widths, that should be half of that. So I need to add numbers together to give me 30, really. And you can check these out, but this will work. 5 plus 25 would give me 30. 12 plus 18 gives me 30. 17 plus 13 gives me 30. And 20 plus 10 gives me 30. So those are the right perimeter numbers. Then we can find the area by taking length times width. 5 times 25 is going to be 125. 12 times 18 is 216, and this is all in square feet. 13 times 17 is 221, and 20 times 10 is 200. Now, my question, after we finish up that whole table, is what length and width will give me the biggest area? And I'm going to say it's not one of them from the table. Right? We know the biggest area, if we are using the fencing for all 4 sides, it's going to have to be a square. And if I've got 60 feet total 60 divided by 4 would give me 15 feet for each side of my square. So if I have a 15 by 15 foot square, that's really an area of 225 square feet. That's the greatest area that I can possibly get. Bigger than anything else that was in the table even. If you drop a ball off a tall cliff, I have this equation. My first question, how tall is the cliff? Right? We should be able to look at this and we should know that the initial height is always the number. It's right here with no variable, no t with it. So this is 250 feet is my initial height. The height after 2 seconds. So I'm going to put a 2 in for the t-squared. I can show this work. You can absolutely use a calculator. So 2 squared is 4 times 16 is 64. So I'm going to have 250 minus 64 is going to give me 186 feet. Okay, my next question is, what about after 3 seconds? Oh, a little too far. After 3 seconds, again, you can just substitute in there, but this would be 250 minus 16 times 3 squared. Well, 3 squared is going to be 9 times 16. You can subtract that from 250. That's going to bring that, that ball down to 106 feet. Okay, and the last one that I have here says, what about after 5 seconds? So if I'm going to change colors, I should have changed colors in between here. The height would be 250 minus 16 times 5 squared. Well, 5 squared is 25, and 25 times 16 is actually 400. So 250 minus 400, that's an issue. That's going to give me negative 150, which doesn't make sense. We don't have a height that's negative 150. What this means is the ball already hit the ground. By the time we get to 5 seconds, the ball had already hit the ground. So it's already on the ground. Right? I want you to understand that if you get, sorry for the bell, if you get a negative height, that means that it already is done. It already hit the ground. All right, same kind of setup here. I just kind of kept them all closer together this time. This time we've got a model rocket. And here's our equation for the height of that model rocket. This one is in meters, and I can tell because of the 5. It really should be 4.9 right there, but instead of having 16t squared, it's got a 5t squared. That's in meters because about 5 meters is the same as 16 feet. So the initial height of the rocket is the 15 meters. The initial velocity is 45. This is really meters per second. And then to find the height after 4 seconds, I'm going to put a 4 into both of the T spots. I'm going to put a 4 right there, and I'm going to put a 4 right there. So I would really have, and this is absolutely a calculator thing then, H equals 15 plus 45 times 4 seconds minus 5 times 4 squared. Okay, and I trust you. I know that you can handle this on your calculator. This would really be, and I don't have a whole lot of space, 15 plus 180 minus 80. That's going to give me a height of 115 meters. Okay, now the rest of these are the same kind of setup. For D, I'm actually just going to do D down here. I've got more space. I'm going to put 8 in there. So the height would be 15 plus 45 times 8 minus 5 times 8 squared. Make sure you're following order of operations or using your calculator very carefully. But when you do all of that work, you're going to get that that is going to be at 55 meters. Now remember, this is launched, right? So it was going up and now it's coming back down. At 4 seconds, it was at 115. At 8 seconds, it's at 55. It's already coming back down. And I'm guessing that you can probably make a prediction about what E is going to be. If at 8 seconds, it's already at 55 meters and it's coming down at 10 seconds, I'm not real hopeful here. I would have that the height would be 15 plus 45 times 10, which would be 450, minus 5 times 10 squared, so 10 squared is 100, times 5 is 500. This gives me negative 35 meters, which means, again, it already hit the ground. Which really means that the height would be at 0 meters, right? We wouldn't have that negative height. All right, one more question. We've got a company that is selling earbuds and they want to figure out what they should charge to maximize their profit, right? So the x-axis on here is the price that they're going to charge. The y-axis is the amount of revenue that they're going to make, and we've got that equation right here. Kind of big numbers, I get that, but part A says, what does the ordered pair 50, and then I know there's extra commas in there, but the X is 50 and then the Y is 1,700,000. What does that mean? If they charge $50 for those earbuds, that's what they would expect for profit. I'd like to type or write a whole sentence there, but I don't have space with how I've got this formatted, I'm sorry. But that's what I want you to understand. If they charge $50, they would get $1,700,000 in revenue. Is there another number that would give us the same amount of revenue? Well, yeah, actually, right here is that same one. So it's probably at about $12, I would guess. Okay. Part B, if the company charges $20 for the earbuds, what should they expect? Now, I can make a prediction from here and say, well, I know it's going to be about, well, it's going to be more than 2 million, but less than 22,500,000. So I would want to actually use the equation and put the 20 in for the X. So this would be Y equals 159,000 times 20 minus 2,500 times 20 squared. And that is, again, absolutely calculator kind of an issue here. That works out to be just over $2 million in profits, which we said that, right? Part C, what price would maximize their revenue? How do they make the most money? Okay, well, this one, I don't need to use the equation or anything. This is the vertex. That is the tallest part of the graph. That means that they should charge $31.80 because it's at the vertex. It'll be maximized at the vertex. It'll make the most money there. The amount of money they'll make is that $2,528,100. And you can check that by substituting in the 31.8 for the X and get what you've got for your maximum profit. Letter D asks what the domain should be. Domain, remember, those are the inputs, the X's. What numbers make sense for the X values? Well, first of all, it wouldn't make any sense to charge a negative amount of money. You can't charge a negative amount of money. And I would not even consider anything like $100 because we're already, if you get beyond this graph, if you go beyond this point right here, you're losing money because that profit then would be down into the negative numbers. That doesn't make any sense. So we're going to say it makes sense, I have to have a different color here, to be between 0 and, I did the math on this, but it's about 63 something, about 64 would be close enough. Okay, those are the numbers that make sense for the domain. Those are also the zeros of the function because that's where it crosses the x-axis. Okay, so if you have any questions about this, please reach out to your teacher, and your test is going to be tomorrow. Good luck.